Hey guys, today we're going to look at the searching algorithms, breadth first search and the depth first search. So why do we need searching? Searching is like the greatest problem in computer science up till today. So you've got a huge amount of data available today, but how do you search through all those data in some particular time? So searching is a great problem today. And due to this problem, as we know, all problems leads to a solution. We know that this has led to a lot of new ideas and data structures out there. So you can put the data into different data structures, use different searching algorithms to do this. So before the Google came up, we had a lot of problems with searching. So it was like in earlier days, you used to give a search query and then wait for like 10 minutes for the search query to come up, the results to come up. What will happen if you had given a wrong search query? Yeah, so your 10 minutes is wasted. But after the dawn of Google came up with a lot of data structures and new ideas to make searching even more effective. Today, you can get your search results in less than 0.3 seconds. So to search the data, we have to store the data in some kind of data structure. In today's topic, for the breadth first and depth first search, we're going to use trees. However, you can also use graphs for these searching techniques, for the breadth first and the depth first searching techniques. Today, we are going to look into the breadth first search and the depth first search for the graph, which is used in graph searching and tree searching. So these algorithms are really useful for a lot of problems. So starting with breadth first search. So we've got B and D. What is B and what is D? So B is the branching factor, that is, each node here has got like 1, 2, and 3. So the branching factor, the highest branching factor is 3. And the depth of this tree is 1, 2, and 3, how long this whole tree goes down. So, however, you will notice that the branching factor is not constant. For example, in this case, the branching factor of node number 1 is 3, but the branching factor of node number 2, 3, and 4 are 2 each. So there are a lot of different problems, and there are a lot of different ways to come up. So while going for the breadth first search, what we do is, this is the first node, 1 is the initial node. From this node, we move on to the second node. So what happens after that? Which node do you search after the second node? You've got the 5, 6, or you can go to the 3. So as the name says, the breadth first search. So in this type of search, we search through the breadth first. So like in this case, we've got 2, and then once we find that 2 is not the node that we are looking for, let's say in this case we are looking for node 6, so we have to now search for a value that is present in the node 6. However, in this case now we are at 2, so we can directly go to 6, but what if it is at 5? We might miss it. So we are following a uniform pattern. So once we finish 2, we'll go into 3. And then we see that 3 is not the answer that we need. And then we go into 4. Yeah, 4. Is it 4 the answer? I don't think so. 4 is not the answer. So what do we do after we finish the first line of depth? So this is D1. So 2, 3, and 4 are depth 1. And then we go into the second depth once we finish traversing the first depth fully. That is node number 5. So is node number 5 the answer? No, node number 5 is not the answer. So the next, what is the next node that we have to search? In this case, as we all know, it's 6. And 6 is the answer we want to, and you had hit on it exactly. So now we are going to look into the properties of the breadth first search. So what are the properties? What I mean by property is the amount of time that it's going to take and the space that is needed. So properties of breadth first search are like the worst case performance, that is, for example, in this case, what if the node is 10? So you have to traverse through all the nodes, and then you have to reach 10. So what if the node that you're searching for is 10? So in that case, you have a worst case performance. So that is B power D. So here in this case, b is the branching factor 1, 2, 3, and d is the depth. Okay, so when you have to reach 10, you have to multiply the branching factor and the depth. So in this case, if the branching factor is same, but in this case, the branching factor is not the same. So how will you do it? It's for you to decide. Next, the worst case space complexity. So in order to in order to find the 10th node, that is if you want the node number 10, how many nodes should you store? You should store 1, 2, 3, 4, and 5, and 6, and 7, 8, and 9 in order to reach 10. But you have to store all these nodes in the queue. Yes. So the worst case performance, as you all have guessed, is big O of B power D. So how do we implement the breadth first search? Implementing the breadth first search is simple. So you can use the queue data structure. Now for the time for assignment. So what you have to do here is find München over here. So starting from Frankfurt, how do you traverse to München? Now next is depth first search. Similarly as in breadth first search, B is the branching factor and D is the depth. So for depth first search, first from tree 1, from node 1, you search node 2. Let's say in this case 9 is what we want. You search for 2, and then you go to 5 instead of going to 3. So once 5, you see that 5 is not the result that you want. You want to 6. Once you finish 6, you have completed searching node 2, so you can remove it from memory, and then you can go to node 3, and then 7 and 8. And then once you finish searching for 8, you know that node 3 is not useful. So you go to node 4, and then you hit on node 9, which is the answer you want. So can you guess the time and space complexity of DFS? Let's start with time complexity. What do you think is the time complexity? Yes, the time complexity of DFS is big O of B power D. So why do we have to use depth first search when we already have breadth first search? The reason is because the space complexity is big O of D. As soon as you finish one particular set of nodes, you can just leave those nodes and go into the second set of nodes. And this is also implemented using Q, but you are free to experiment with any other type of data structures that you feel. Here is the answer to the breadth first assignment that was posted. So how do you go to München? Is first you search from Mannheim, and then Würzburg, Kassel, Karlsruhe, Nuremberg, Erfurt, and then finally you reach München. So now are you sure you know BFS and DFS? Okay, let me ask a few questions. What will you do if there is a loop in DFS, just as the problem that was posted to you for the BFS? What are the data structures to use? Second question. In order to reduce the space complexity of BFS, why don't we just delete all the nodes that are visited until the previous depth, so that you don't have to remember all the nodes and reduce the space complexity of BFS too? Can you do it? These questions right now, I don't have the answer for them. I haven't posted it up in the slides, but it is for you to explore and find out. Thank you guys. That's the end of the presentation, and I'm Raj.